Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. I mean, okay, so technically I'm a little bit behind my schedule. So like today I'm really talking about real quadratic forms. I may get to calculus of many variables today. We'll see. I'm in no hurry. We got plenty of time. It was pointed out to me that there's a Math 311 test the same day as my test 3, but I really don't think I can move test 3 in good conscience because I'll be gone here because some ex-students of mine invited me to give a talk at Arkansas, so I'll be gone that day. And so I'm not sure what we're going to do Wednesday exactly. I have to look up. I filled out a form and said what we were going to do, but I can't remember what it was. I'll probably move quiz 3. Probably move quiz 3 to Wednesday and just give you guys more time. So it'll be, but Nathaniel has something he might want to talk about to you guys. Nathaniel's been working on PageRank. If you guys would like to see how linear algebra explains how Google works, that might be interesting. So we should. What do you guys think? Should we do so? Choose your own adventure. Would you rather listen to Nathaniel talk about PageRank and Google on Wednesday? Give him the whole time.
What's the other option?
The quiz 3 on Wednesday.
And Friday?
No, I just won. No, and then Friday. Then Friday, I would come and talk about quiz 3.
Wait, why are we taking quiz?
Hmm?
I'm sorry. What is quiz 3 on? No, what is it? What? Okay, if Nathaniel talks about Google.
Quiz 3 is on linear algebra.
Yeah, if Nathaniel talks about Google, what day are we taking the quiz?
Friday.
Okay. I was just curious.
So I mean, if you guys don't listen to Nathaniel, that bumps the quiz up one day.
And that means we can ask questions on Friday before.
It gives you more time to ask questions on Friday. Yeah.
Why can't we take the quiz and listen to him?
That's another option. Make Nathaniel talk faster. Does that sound good? All right. We're going to go for robbing some of Nathaniel's time away from him. So quiz 3 and Nathaniel will give a how many minute talk on PageRank?
It can be so if the quiz takes half the time, I can take the rest of the time, so 25-minute session.
25 minutes? All right. It's a plan.
Or do we get 20 minutes for the quiz? Isn't it 30?
Oh, is it? Okay, that's fine.
Nathaniel has 20 minutes to talk about PageRank, 30 minutes for the quiz. Yeah. What?
Is the mission still due Friday then? Even though
We can keep the mission being due Friday. That's fine. Yeah.
Is that what we can ask questions about the mission that day as well? No. Like we can turn it in. Can this be sent as an email?
Yes, I will send an email about these.
Okay.
I mean, an announcement. I will post an announcement on these things. Okay. So now let us get back to something more interesting. And so I sent you guys a link. Let me close this there. Better. I feel much better now. All right, so check this out. So what you're looking at is a conic section. Do you guys know what a conic section is? Why is it called a conic? Cross-section of a cone. Yeah. Let me foolishly attempt a picture. But yeah, that's what it means. Section is like a fancy term for cut. And so a conic section is formed from cutting a cone, but it's not the kind of cone that you can get at Mr. Goody's. It's I shouldn't have started that. Let's see here. I've now lost the audience for the rest of the time. So it's a double cone, and if you slice a double cone with a plane, that gives you conic sections. So there's different ways you could cut it. Like if you just cut it vertical, then just like a straight vertical section, you just have the lines. You'd get a pair of lines through the origin. If you took the plane and cut it just like this, you'd get just the interior point, just the middle of the intersection point. So lines and a point. These are examples of so-called degenerate conics. But the interesting conic sections are, of course, like I won't even try to draw it, but if you can slice up here, and you only hit one of the cones, in this double cone, you get a parabola. If you, that's one, if you slice it like that. If you slice it like this, you get an ellipse, right? And then there's another kind of plane that will cut through both and get hyperbolas, all right? I will not attempt to draw it, but I will show you over here. So that's one definition of conic section. A much more convenient definition of conic section for the purpose of, mathematical analysis is that a conic section is any solution to a second degree polynomial equation, as I have right here. So ax squared plus bxy plus cy squared plus dx plus fy plus g equals to 0. The solution set to such an equation is called a conic section. And so what I did here was, add some sliders so that we can vary the values for a, b, c, d, e, f, and g, and see that you can get all kinds of different hyperbolas and ellipses. And oh man, it was working better earlier. My choice of, let me pause the A here. Start again. There, maybe that would be better. So as you can see, sometimes it's, depending on the values of A, B, C, and D and G, and you get different things, right? Hyperbolas or ellipses. And you notice that they're possibly what? Like tilted, right? So let me stop this. Stop this. Let's see here. All right, so if you think about it, you can, if you think about it, right, you could complete the square, right? If you take that equation up here, you could take this dx term and this fy term and lump them in to an a times x minus h squared and a c times y minus k squared, right? Now, you could also rewrite this bxy as what? I mean, not the same b, but I'll do it as b just for the sake of illustration. All right. So let's see here. So the HK, what is that? Let's see here. What happens if we let HK go around? What's going on here? What is HK? It's that gives us the center of the conic section, right? So basically, we can shift x to x minus h, y to y minus k, and look at, generically speaking, ax squared, a times x minus h squared plus b times this times y plus c times that equals to a constant. That gives me a conic section centered at hk, right? Now, let me stop moving that around. Let's fool around with, come on, I'm trying to make this bigger. I don't know. Oh, there we go. So I put it equal to r. Let's put that r equal to 1 just for the sake of discussion here. Now what happens if I put b equal to 0? Let's think about that. If we put b equal to 0, what's that do? Uh-oh. Look at that. So we got nothing. Does that make sense? So look at this. C is negative. See this? A is negative. C is negative. B is 0. So we're looking at the solution set of minus x minus h squared minus y minus k squared equals to a positive constant. Of course there's no solution, right? You can't have two negative things added together to give you 1. But on the other hand, if I was to take A and make it positive, well, the other one's negative. That gives me a hyperbola which opens sideways, right? On the flip side, if I take the C and make it positive, at the same time I get an ellipse, right? If I take the C, keep it positive, and make the A negative, we get a hyperbola which opens the other way. So depending on how you've got, plus minus equal to 1 or minus plus equal to 1, we either get an upward opening or a sideways opening hyperbola, right? provided that the middle term is 0, the hyperbolas are what? They're parallel to the coordinate axes. But what happens, and we can animate A and B to A and C to see what happens there, right? So you get hyperbolas and then no solution when they're both negative, and then you get hyperbolas and you get ellipse a little bit. If I make this bigger, we can get bigger circles. All right, now what happens though if we let B be, say, 1? You see what happens to the ellipse now? What can you see what happened? What happened to that ellipse? It's no longer parallel to the coordinate axis, right? It's rotated. So the major axis is like this, right? And the minor axis is like that. And they're not parallel to the coordinate axes anymore. Let's see here if I can. So it doesn't really matter how I change A. They're all kind of rotated, right? See that? They're rotated different ways, but now if I change this B, it's going to, it's funny. Look at that. Rotated a different way. But unless I get B equal to 0, they're going to be rotated, right? So that's nearly a circle. If I get A and C equal, then we get a circle, which is a special kind of conic section, of course. And we can move the thing around, right? So there you go. I'll center it. We usually center them where? The origin. So I just wanted to play with this for a couple minutes to make sure that you have a well-developed sense of what is a conic section, what do they look like, what are the possibilities, right? The possibilities are...
You just type in 0, by the way. You don't have to scale it.
Oh, I can type in 0?
Like if you hit the box there, yeah.
But now it's created a... Uh-oh. Well, anyway.
Click outside the box.
Well, it doesn't matter. Anyway, this, I spent, listen, it took me all of 15 seconds to create this page, so it's not like a big deal or anything, right? I mean, Dr. Scambordis was telling me about his day when I made this. It wasn't a big deal, So, what? I'm saying that it doesn't require a lot of mental effort. I can completely listen to Dr. Scambordis and do this at the same time is my point. I'm not, you're misconstruing my words. You're misconstruing my words. Okay, so, listen, the long story short of it is we just want to, okay, so we can always complete the square to center it, basically to make it look like it's centered at the origin, right? So we're going to focus our attention on that case. This gives us what's called a quadratic form. So, definition, Q from, let's say, Rn to R, where Q of X is equal to X transpose, AX, and A transpose equals to A is called a quadratic form. Now, there are more pure ways of defining this, but I'm just making a pragmatic definition, a quadratic form, and with matrix A. And we also might use this notation. The matrix of Q is equal to A. So this is a different use of the standard matrix notation. Hopefully there's no danger for confusion. A quadratic form is not a linear transformation. It's something else, all right? So first order of business here is for me just to show you an example. So if we look at Q of, say, x1, x2 equal to x1 squared plus 2x1, x2 plus x2 squared, this is an example of a quadratic form. Let me show you why. We can rewrite this as x1 x2. So that's a row vector times a particular matrix. So I'm going to let you guys tell me what matrix goes there. I've grown impatient with your guessing. We put a 1 here. We put a 1 here. All right. And actually, we're going to put a 1 here and a 1 here. This is not great in terms of seeing which one went where. So if you don't mind, I'm going to do an example 2, which is got a little bit more to it. And so here we go. And this time I'll use, okay, x1, x2, and I'll do 3x1 squared plus, I don't know, 8x1, x2 minus 9x2 squared. All right. Let's see here. This is equal to x1, x2 times a matrix times x1, x2 again, this time as a column. All right, so now I can kind of, that 3 puts a 3 here, all right? This minus 9 puts a minus 9 down here. And then for the 8, we'll take half of whatever the middle thing is, and we put it, so this 8, right, puts a 4 here and a 4 there. Now, pragmatically speaking, you might be like, well, I don't have to put a 4 there and there. I could put an 8 in one of the places you wrote a 4, and it would give you the same formula. You're right, but we insist that the matrix of a quadratic form is symmetric. Why would we do that? Why do we want the matrix of the quadratic form to be symmetric? That gives us license to use what theorem on this thing? Remember? The real spectral theorem, right? Because that means that the matrix that we're looking at, both of these, is orthonormally diagonalizable, right? See here, example 3. Let's see here. Let's suppose we have q of x, y, z equal to, the phone suicidal? Seems like it's lost its will to stay on the desk. I don't know why you guys are laughing. It's nothing to make fun of. You monsters. Sorry, I should behave. All right, so, oh, I never gave you a formula, did I?
No.
Let's work the other way. Let's suppose we do 3, 1, 1, 2, 2, 4, 5, 5, pi. Yeah, I didn't see that coming, did you? Let's see here. So then this works out to 3x squared plus 4y squared plus pi z squared plus 2xy plus 4xz plus 10 yz. And if you understand how to multiply it out, you should understand how to invent the matrix, right? So it's always like double whatever the off diagonals are, go to build that sort of cross term, right? And, okay. So, so we need to investigate. What the orthonormal eigenbasis does for us. So here, if I'm using x as a scalar variable, perhaps I should look at this as being like v transpose, and this as being v, right? Because it's kind of bad form to also call that x, right? So, all right. So let's suppose that our orthonormal eigenbasis is beta, which is, v1, v2, vn, all right? And it's a orthonormal eigenbasis. So what's that mean? With orthonormal eigenbasis for A. So here I'm thinking of A as being an n by n matrix, all right? The things we're about to derive are going to be true for a 2 by 2 matrix. They're going to be true for a 3 by 3 matrix, Okay, so what does that mean, eigenbasis? That means that A times Vi is lambda I Vi, right? And because this is a real symmetric matrix, we know that the eigenvalues are real, all right? And they exist. They could be repeated, but they're real. I'll say for lambda 2 through lambda n in the reals, right? And what does the orthonormal give us? What does that tell us, the orthonormality? Yeah, the length of, okay, great. The length of each vector is 1. Absolutely true. We also know that Vi transpose Vj is the dot product of Vi with Vj, right? And this is our beloved Kronecker delta Ij. Can you tell me what it means in terms of the matrix for this basis? Like the matrix, the beta, if we concatenate like this, right? What can you say about this matrix? We worked this out the other day. What happens if we calculate beta transpose times beta again, the matrix here? Yeah, we get the identity matrix, right? So the matrix, the basis matrix for this matrix is an element of the orthogonal n by n matrices, right? An orthogonal matrix has columns which are orthonormal, form an orthonormal basis. All right, now I'm going to jog your memory a little bit more. Do you remember we talked about how to calculate coordinates with respect to a basis in Rn? How did we do that? Like if I asked you, what is phi beta of x? What would we call that x bar, let's say. What was our formula? Remember our formula for coordinate vectors? Coordinate vector in Rn, it was what? It was beta inverse times x, right? This was how we calculate the coordinates of x. It was the inverse. But what does the thing right above that say? It says that the transpose is equal to the inverse. So to calculate the coordinates with respect to the eigenbasis here, orthonormal eigenbasis, we just calculate the transpose of the matrix and multiply it by x. This is very neat. These, in this context, are called eigencoordinates. So let's rewrite the formula. Let's express the formula for our quadratic form in terms of eigencoordinates. In other words, I want to trade what? I want to trade my x's for x bars, right? So can you guys tell me how to solve what I wrote down here for x? How do I solve this for x? It's what? Yeah, basis, it's the matrix for the basis times x bar, times the eigencoordinates, right? Just multiply both sides by that. And so I'm going to use that over here. See what I've got is I've got the basis times x bar transpose the basis matrix times x again. And what do? I forgot my bar on the x here. My bad. So then socks, shoes, right? And okay, great. So that's x bar transpose of that a beta again. Now let me make it look. Make it look more familiar to you. If we call the well, excuse me. Oh, I don't know what's the best way to convince you here at the moment. What is this? What is this? Maybe we should just work it out. What is a times beta? So that's a times v1, a times v2, a times vn, right? But these are all eigenvectors, so that's lambda 1 v1, lambda 2 v2, lambda n vn. What happens when I multiply that by, this transpose? So that's v1 transpose, v2 transpose, vn transpose times this. So if you look at it, right, if you calculate the ijth entry of that matrix, let me do that. What's the ijth entry of this matrix that I'm looking at? It's what? It's V I transpose times lambda j Vj. Lambda's a constant. We can pull it out. And then we've got Vi transpose Vj, also known as Chronic or delta Ij, right? Sorry, Nathaniel. I know this red stops being visible where you're sitting, at right about there. Okay, sorry about that. I should throw these out. Anyway, my point to you guys is what we're looking at actually is, let me write it this way, x bar 1, x bar 2, x bar n. And then this is a diagonal matrix with the eigenvalues down the diagonal. I mean, that's what happens if we sandwich the matrix between the transpose of the eigen basis matrix and the eigen basis matrix itself. That similarity transforms the matrix A to its diagonal form with eigenvalues on the diagonal. And that's what we got. And that's really cool because that means that this is just lambda 1 x bar 1 squared plus lambda 2 x bar 2 squared plus plus lambda n x bar n squared. So in the eigencoordinates, the formula for the quadratic form is most beautiful. What's missing? The thing we were looking at in the, my pictures, the start of today, we saw that when there were cross terms, right, when there are terms that aren't just squares of the coordinates involved, that leads to, like when we set this equal to a constant, it leads to rotated things. And that's not present here. So in the eigen coordinates, the formula is, again, most beautiful. Now, you're like, well, you've shifted gears. The start of today, you were looking at an equation. Now you're looking at an expression, right? So how do you get conic sections from this? So notice, so here's an observation for you. Q of, xy equal to, constant gives conic section centered at origin. So, like, generically speaking, what does that look like? So this is something like ax squared plus bxy plus cy squared equals to, equals to d. And for convenience, it helps if we put a 2 here. The reason to put a 2 here is because then we can look at it this way. This is xy, a, b, b, c, xy, like that, right? And I can look at that as the matrix of the quadratic form. So when is it going to be an ellipse? When is it going to be a hyperbola? When is it going to be a parabola? Right? So this, suppose that, so if we adopt in eigen coordinates, what does it look like? It looks like lambda 1 x bar squared, right, plus lambda 2 y bar squared equals to some constant d. So you guys tell me, I guess we need to, for the sake of discussion, let's put d positive just for the sake of, I mean, you could put d equal to 1. Let's put d equals to 1 here, just for the sake of being nice. Lambda 1 x bar squared plus lambda 2 y bar squared equals to 1. What does that look like in the, I mean, my question to you, is that an ellipse? Is that a hyperbola? Is it a parabola? Can you tell me? It could be a circle, it could be an ellipse, it could be, let me suggest to you this. Lambda 1, lambda 2 equals to 0 implies parabola. Lambda 1, lambda 2 less than 0 implies hyperbola. Lambda 1, lambda 2, but lambda 1 and lambda 2, both positive, implies ellipse. And finally, lambda 1, lambda 2, both negative, implies no solution at all, as we saw. See, if one of them or the other is 0, the equation is just like number times x bar squared equal to constant. Oh, wait a minute. That's not a parabola. What is that? Duh. What if lambda 1 equals to 0 and lambda 2 equals to 3? You'd have what? You have 3 y bar squared equals to 1. What's that? That's y bar is equal to plus or minus 1 over root 3, yeah? That's not a parabola. That's a horizontal. Well, it's a pair of lines. They're generally going to be rotated with respect to the original xy coordinate system. To see parabolas, I think I need I'm trying to think here. I think I need the I'm not sure how to see parabolas in all this at the moment. I get a pair of lines. Parabolas. Excuse me. Of course, parabola. You know, this is a parabola, right? So if I've removed y by completing the square, I'm not going to see a parabola in this particular discussion. I am okay. I have a cold, but it's okay. Please go home. It's very considerate of you. I'll stay up here. You stay back there. Let's see here. Listen, so let me be more specific. My example 1. My example 2. If I put these quadratic forms equal to 1, what kind of curve is it? Right? In other words, if I look at, so example 1 in our usual notation is what? It's x squared plus 2xy plus y squared equals to 1, right? So what's that? I heard ellipse. I heard parabola. I think you're both wrong. Yeah. So you notice we can answer the question by calculating the eigenvalues. How do you calculate the eigenvalues of a 2 by 2 matrix? Well, you know how to do that, right? What are the eigenvalues here? Well, the plus or minus 1, I think 0 is an eigenvalue for that because it's not invertible. Right? If the matrix is not invertible, 0 is an eigenvalue. I guess you guys are going to make me calculate it, huh? 1 minus lambda, 1, 1, 1 minus lambda. Determinant. Lambda minus 1 squared minus 1. So that's lambda minus 2 times lambda. So 2 and 0 are the eigenvalues. Two and 0 are the eigenvalues here, I think. What's that? It is a pair of lines, right? Which becomes, I mean, now that I say that, everyone probably will see, oh, this is x plus y quantity squared equals to 1, right? So y is equal to minus x plus or minus 1. Yeah? There's the lines. But we anticipated that by calculating the eigenvalues. If one of them is 0, then that means it's a pair of lines. More specifically, though, it means that you can rewrite, I mean, more to the point, this is equal to 2 x bar squared for some choice of coordinate. Eigencoordinate. There's an eigencoordinate x bar because it doesn't have any y bar dependence. This one here, what's this? If I put this equal to 1, what am I looking at? So the question is, what's the eigenvalues of 3, 4, 4 minus 9, yeah? What? Oh, come on. I hit the wrong button. Oh, by the way, a quick check on your eigenvalues. Remember what we learned last time? The determinant of the matrix should be the product of the eigenvalues. The determinant of this is 0. Product of our eigenvalues, 0 and 2, is 0. The sum of the eigenvalues should be the trace. The trace of this matrix is 2. The sum of the eigenvalues, 0 plus 2 is 2. That checks our work. Here, I look at this. The sum of the eigenvalues should be minus 6. The product of the eigenvalues, right? The product of the eigenvalues is what? What did you say? Minus what? Minus 27 minus 16, what's that? Minus 43. So if you want to play this game, you can. You can take this 2 equations and 2 unknowns and solve. Okay? So this makes lambda 1 what? Minus 6 minus lambda 2. I mean, admittedly, this is harder than just factoring the stupid quadratic, but come on. Come back. Come back. I wanted to do something. Okay. So what I'm trying to get across to you guys, there's different stages of playing. I mean, there's okay, so to actually find the explicit eigencoordinates, what does that take? You actually have to, first of all, calculate the eigenvalues for the quadratic form. Then you have to find the complete orthonormal eigenbasis for the matrix, right? Once you have that, though, you can find explicit formulas for the rotated coordinates, which take the formula for the quadratic form and remove cross terms and make it just the sum of, you know, the eigencoordinates squared, with the weights already being known in advance to you as the eigenvalues. So this is very nice. Now I would also remind you, you know, as we fuss with homework, we should remember that there's a website that is helpful. I mean, of course, you could use MATLAB or Mathematica, blah blah blah, but we could also use this. So I like the old version. So what matrix we were just messing with? What, 3? Admittedly, this is wasteful. We could have calculated this by now, by hand. But as you can see, it's ugly. Ugly. The eigenvalues are minus 10 and 4.2. But from that, I can see that there exists a coordinate system that looks like essentially minus 10.2 x bar squared plus 4.2 y bar squared. And so if I set this equal to 1, it's a hyperbola, which opens parallel to the x bar, y bar rotated coordinate system. And I can see that without doing a bunch of calculations. Like, this is just the theory tells me that without getting into all of the details of how to actually do it. All right, so let's look at the notes here for a second. I have some, in the notes I actually have some gory examples with all the details on what I'm talking about right now. Now, in the notes, I also look at a 3-dimensional problem, right? I've been talking to you for the last few minutes about what happens if we put the quadratic form equal to a constant, right? That gives us a curve in the plane. But we can also take a quadratic form in 2 variables and set z equal to that. Then that's going to give us a graph in 3 dimensions. If we have a quadratic form in 3 variables, and we set that equal to a constant, that's going to give us a level surface. There's a lot of different games we can play here with quadratic forms to construct different things. But here is z equals to x squared plus y squared. You might recognize this from Calculus 3. This is the, what is it? This is the paraboloid, right? Ah, no! The accursed rapid scrolling has got me again. I'm not used to that yet. On the other hand, if you look at z equals to this, it gives us, what is this thing called? Hyperboloid. Here is a, so here's what I was thinking about. I was thinking about this is each one of these is a parabola z equals to q of xy, but it's not. If we take any particular z, we get a pair of lines, which is what we were seeing in our discussion today. All right. Here is what I was advertising a second ago. This is a quadratic form in 3 variables, x squared plus 2y squared plus 3z squared. If you set this equal to a constant, we get what's called an ellipsoid. All right. With with the sort of principal radii of 1 and square root of 2 and 1 over square root of 2, I think, and 1 over square root of 3, if I remember right. And if you look at this equal to different constants, right? What if you allow, instead of just one constant, you allow different constants? Then you get different ellipsoids, bigger and bigger, and they're like an onion fill space. You think about this. This is the theorem we proved today, right? If you have a quadratic form with eigenvalues lambda 1 through lambda n, then you can recast the formula in eigencoordinates just like this. Instead of using x bar, I used y's here, all right? Now, so here's a specific example. I have a quadratic form in 2 variables, x and y. All right, here's the matrix. And that has eigenvalues 1 and 3. Before I even do anything else, I can tell you the formula for this in eigencoordinates is x bar squared plus 3y bar squared, because the eigenvalues are 1 and 3. But to actually find those formulas and how they relate to the standard Cartesian coordinates, it's also straightforward. All you have to do is find the eigenvectors, normalize them so that it's an orthonormal basis. And so here's specifically how x and y relate to x bar and y bar, or vice versa, how x bar relates to x and y. And you can take these formulas, well, these ones, and plug them back up into the original formula, and all of the cross terms will just go away. They cancel out. It's really neat to actually do it. And you get this, like I said a minute ago. So here's the formula for the quadratic form. And I put a tilde here because technically it's a different function. Anyway, if we put this equal to a positive constant, it's an ellipse, right? So, and here's a picture of it. Well, not really. What is this a picture of? I think this is a picture of z equal to that. So if you just put z equals to, like 2x squared plus 3y squared, it gives you an elliptic paraboloid, like the sections of it, horizontal sections of it are ellipses. This is that as well, but it's rotated by 45 degrees. If you can't see anything in those pictures, it's okay, but Hey, here's my first example from class today, and here is the explicit change of coordinates that you need to do using the eigenvectors, putting together the change of coordinates using eigenvectors, relating x to x bar and y bar, and as I told you, in the eigencoordinate system, it gives you 2y bar squared. And here's the details of that. Now, one of the things I like to point out here is you studied this since you've been studying geometry, y equals 1 over x, right? As a quadratic form, that's xy equals to 1, right? So that is this. But the matrix for this quadratic form is 0, 1 half, 1 half, 0. What are the eigenvalues? They're plus or minus a half. That's because this is a hyperbola, rotated 45 degrees. And in here, I put a 4 to get rid of the half. But as you can see, the change of coordinates takes that 4xy, and in the x bar y bar coordinate system, it becomes something that's manifestly a hyperbola if you set it equal to a constant. Oh, I seem to be out of time. But anyway, I hope that gives you an insight on how to do these problems. It's really a straightforward and beautiful application of what we've already talked about. So next time we'll talk about Calculus 3 and how to derive the second derivative test from what we're doing. So thanks, guys.